Hello, this is Sean Kelly, and this is material from Chapter 2. So we will be going over the material that you need to know from Chapter 2, including the phases of the moon and the seasons. So this is a pretty important chapter for us. So we're going to start off pretty pictures, Astronomy has lots of pretty pictures. Don't forget to go to the astronomy picture of the day. And of course, when we look up at the sky, we see the stars moving through the sky. By the way, tonight will be a pretty awesome conjunction between Venus and Mercury. Maybe I'll show you that in just a few minutes. But they'll be right next to each other in the sky. It's pretty cool. So I managed to see Mercury last night. Mercury is very difficult to see because it's quite a bit dimmer than Venus. But if you look, they'll be right next to each other tonight. Good opportunity. So when we watch the patterns of the sky, one of the cool things to understand about astronomy is that everything about time is based on astronomy. So if you think about it, one revolution of the Earth around the sun is what we call a year. But even a day, right? A day is one rotation of the Earth, 24 hours. And we see the sun rising in the east and setting in the west. But it's not just the sun, it turns out it's the stars as well. So let's go ahead and switch to our software. I'm using Stellarium. And in Stellarium, I have a nice view here. We can take a look at the sun over here. I've dialed up 6 o'clock in the morning. And you can see it's over in the east. It's not exactly in the east, actually. In fact, today's sun and moon, right? We're a little bit to the north of east, and that is kind of important, but not a big deal right now. So if we watch through the day, right, we can see the sun go higher in the sky. It's highest when it's directly over south, which is actually called the local meridian, and that happens at about 1 o'clock, as a matter of fact, because we are in daylight savings time. I did tell you last time, actually, we can find the middle of the skyline if we go to sky and viewing options. Markings meridian, that's how you get the line in the middle of the sky. So when the sun is on that line, it is called local noon. Again, it happens at about 1 o'clock. And as you advance through the sky, you can see the sun is setting in the west. Okay, so rising in the east and setting in the west. And then come the stars. Here they come. And it's the same thing, the stars rise in the east and they follow a path. So I can actually just play here. We can just play and we can speed it up a little bit. And we can watch the stars and the sun move. So first the sun, daytime, and then the stars, nighttime. Now, we're looking towards the south right now. What would happen if we looked towards the north? Well, you might notice something kind of interesting. That's kind of fast, isn't it? It looks like I can't change. Ah, there we go. A little bit. Not quite as fast. Okay. There we go. Slowly. One more time. There we go. That's a little bit too fast, but oh well. There we go. So if we look to the north, you might see when the sun goes down, look at the stars, look at them go. You might notice that there's one star that's not moving. Anybody want to guess what that is? Okay, and if you guessed Polaris, you'd be correct. It's called the pole star, the North Star. You'll notice that north is right underneath it. Now, actually, the real reason is that there is a sphere of stars going around us. Well, that's what we see, and we call this the celestial sphere. So I'm going to turn that on right here. There's a little icon to turn it on, and I'm going to turn off the ground and the atmosphere to show you the celestial sphere. So here is the celestial sphere, and you'll see that it has, there's the point up here that the whole sky seems to be turning around. That's called the North Celestial Pole, and there's another one down here beneath south, and that's called the South Celestial Pole. So we can see that all the stars are rotating around the Earth. Well, that's what we see. So why is that happening, right? What's going on? Why is that happening? And the answer is, well, because we're standing on a globe that is rotating. So here's our globe. And just so you understand, if I look at the globe, just to remind you, here is the United States, and we have the West Coast here and the East Coast here. And it turns out that we see the stars moving from east to west. But the reason is because the globe is moving towards the east. So make sure you write that down. The direction of the Earth rotation is towards the east. And because we're standing on this moving globe, we look up and see the stars moving in the opposite direction. Okay, that's kind of a neat little fact. You may or may not have known that. Okay, so the stars are moving because we are on a rotating sphere. So the sphere of stars around the Earth is actually going to be exactly the same orientation. So right above the North Pole will be the North Celestial Pole. Right below the South Pole will be the South Celestial Pole. And above the equator will be the celestial equator. Let's go back to our software again, and I'm going to show you some cool stuff. Okay, so let's turn the ground back on again. And I've turned off the app. Oh, oh, wow. Okay, let's see. There we go. Let's go back to our story here. I'm going to show you kind of an important thing. First of all, the celestial sphere, which goes around the Earth. If you look, you'll notice something very interesting. I'm going to go to this options again and turn on the celestial equator. Let's see if I can find celestial equator. Anybody find this? Where is the equator? Celestial equator. Huh. Oh, let's see. Maybe this one. Is that this? Okay. I think so. Actually, let's change the color. Celestial equator. I think that was it though. Let's make it yellow. Aha. Okay, now I can see it really brilliantly. Okay, so I want you to notice something kind of important. The celestial equator comes right out of the east and goes all the way to the W to the west. Okay, that's the celestial equator. Now you'll notice that actually at this moment, whatever the date is, this looks like 527. Okay, is the sun above or below the celestial equator? And the answer is we call that above. So this celestial equator is kind of like the equator of the Earth. Instead of longitude, though, what we measure around the equator, the celestial equator, is called the right ascension. So if you look right here, you might notice something. It says 0H, 1H, 2, 3, 4H, 5H, all the way to 23H. So anybody understand that? It goes from 0 to 24. These are 24 hours in a day. And so each one of these lines right here on the celestial sphere is called an hour line, an hour circle of right ascension. Right ascension is the word. As you go above or below the equator, the celestial equator, that would be like latitude on the Earth. This is called the declination. So declination is positive, positive 10, positive 20, positive 30, or negative if you go below it, negative 10, negative 20, negative 30. You don't have to know a lot about that. But if the sun is above, we say it has a positive declination. And if you notice what happens when I play this, right, is the sun is actually going to follow a circle. It's actually on a circle today. It's on one of the lines of the celestial sphere. And so it's actually moving around in circles. In fact, the stars are always just moving around on circles. The problem is we can't always see the full circle. Okay? We can't always see the full circle. So if you do watch the stars near the North Celestial Pole, which is right where Polaris is, it's not exactly where it is, it's right next to it. It's the best star we have right now. But if you watch those stars, what direction do they move? And the way we describe it is the way we talk about clocks. They go against the clock, so it's called counterclockwise. So around the North Celestial Pole, the stars move in a counterclockwise circle. What about the South Celestial Pole? So if I zoom back out and I go to the other pole, which normally I can't see, by the way, because it's below the horizon. But the South Celestial Pole, the stars are going to move on clockwise circles. Okay. Let's go back to our share here. Okay, we'll go back to our PowerPoint. So let's see what we've got. We've got the word rotation. You need to know what rotation is. Rotation of the Earth is the spinning of an object around an internal axis. The rotation of the Earth has a period, that's the length of time, that it takes to do one cycle, and the period is 24 hours. The revolution is the motion of the Earth around the sun, for example, or the moon around the Earth. And that takes 1 year for the Earth to go once around the sun. Does anybody remember how much time it takes the moon to go once around the Earth? That is called 1 month. It's about 1 month. We'll talk about the exact time in a minute. Okay, the horizon is the line between the sky and the ground. And latitude, longitude, we talked about that. That is on the Earth, right? On the surface of the Earth, how we measure the position. But if you're using the sky, when we look at the sky, we have these words called azimuth and altitude, and they're going to be important for us today. The azimuth is measured from the north direction, right? From north on the horizon. And as you go around the horizon, there's 360 degrees altogether. When you get to east, you have 90 degrees azimuth. When you get to south, it's 180 degrees azimuth. When you get to west, it's 270 degrees azimuth. Back to north is 360 or back to 0 again. Altitude is the angle above the horizon. And so if you are on the horizon, that's a 0 degree altitude. If you get to the highest place you can in the sky, the point right above your head, that's known as the zenith point. That would be an altitude of 90 degrees. Okay, so what you see depends really strongly in a single day, on 1 day, right? The location of the sun is not going to be the same for everybody on Earth. It depends on where you are. So if you are standing, at different positions on the Earth, you will see the sun at a different altitude. So your latitude on Earth affects the position of the sun. Longitude does as well, but mainly it just shifts it forward or backwards an hour. It doesn't change the maximum altitude. So I actually want to demonstrate that to you. So let's go ahead and go back to our application. Let me stop this, try it again. Let's go to our stellarium. And that's getting confusing. Let's pause, okay. Let's turn the ground back on. And you can see I was looking underground. And then let's turn the atmosphere back on. Okay, so what I want to do is let's bring the, let's turn off this grid. And I'll turn off my, my equator again. And I'll turn off my room. I'll leave the meridian. We'll leave the meridian. We want that. Okay, so I'm going to turn the atmosphere back on. Oh, it's on. Okay, and we'll go ahead and move forward in time to when the sun is up. Here comes the sun, doo-doo-doo-doo. And so on this day, 6/20, which is actually a very interesting day, we'll talk about that in a little bit. Actually, 6/21 is the usual date. There we go. So the sun is reaching its highest point actually when the azimuth is 180 degrees. Okay, so I can see here azimuth of the sun. I need to put that 179. Okay, let me wait a couple more minutes. Oh, there it is, 180. So at 101 on the 20th of June, the sun will be crossing the meridian or at the highest point in the sky. Now, if I change my location, let's change our location. Let's move to someplace to the north. Okay, so now my question to you, see if you can answer this, make a guess. If I move north to someplace north, will the sun be higher or lower in the sky because of that? And the answer is same time, right? All I've done is move north. Oh, look at that. The sun is lower in the sky. So I want to go ahead and move back to that time when the sun was crossing. And you'll see that on this day, I'm very far north, by the way. On this day, the sun is crossing the middle of the sky at actually at 12 o'clock. Interesting. I'm not sure why that is, but don't worry too much. Let's look at the altitude right here. It's only 38 degrees. It's much lower in the sky than it was, okay, when I was in Santa Barbara. So if I go back to Santa Barbara, back home, how do I do that again? Return to default location, okay. Return to default, oh, that didn't work. Go back to Santa Barbara, California, Santa Barbara. There we go. Santa Barbara, United States. Okay, and we were back home. And if we take a look right here, there's our sun high in the sky. Let's put it back. And instead of 38, you can see it's at about 79 degrees. Okay, that's very, very different. So the changing the latitude on Earth changes the position of the sun in the sky. Okay, so back to our slideshow. So we understand that idea. On a single day, the altitude of the sun is different for different people at different positions on the Earth. Okay, but we also see changes in the sun throughout time, right? The author wants to make sure you know that we can't see as much of the sky at night as we used to in the old days because there's so much more light pollution. And so you look for the dark areas. Somebody asked, where would you want to go in California? One of the best places is Death Valley or Joshua Tree. Those are wonderful places. And you want to look for a new moon, and you will be blown away by the Milky Way in the evening. You're going to stay up late and watch the Milky Way, and you will cry. It will be so beautiful. It'll be amazing. Okay, so here's our celestial sphere. We mentioned it already. It's got a north pole and a south pole and an equator, just like the Earth. And they're actually just extensions of the Earth coordinate system. So right above the North Pole is the North Celestial Pole. That's where you find Polaris, right? Right next to that. And below the South Pole of the Earth, the South Celestial Pole. Above the equator of the Earth, the celestial equator. Okay. And we mentioned this already, but if you watch the stars near the North Celestial Pole, they rotate in a counterclockwise direction. Okay. The further away you are from the pole, the larger the circle is. So when we see the sun making an arc, we don't see the full circle because the circle's too big, right? But there are some stars that are close to the pole that we can see them moving, and we'll talk about that in just a minute. But those, the constellations that are near the pole are called circumpolar constellations. So if you could see the South Celestial Pole, you would see the stars moving in the opposite direction. Okay. Now, there is no star there. A lot of times people ask that, is there a South Star? There's no South Star, but there are constellations that people use that for example, there's one called the Southern Cross, and it points right towards the South Celestial Pole. I could actually show you that. If you're interested, make sure you ask me. Okay, so we mentioned the celestial meridian. That's a local meridian that cuts the sky in half. And I also mentioned the words before. Right ascension is like longitude on the celestial sphere. It's measured in hours and minutes, and it's called hours and minutes of right ascension. Then you measure around or along the celestial equator. The declination is a measurement like latitude was on the Earth. You either go above the celestial equator or below the celestial equator. So above is positive declination, below is negative declination. Okay, so something kind of important to know in astronomy, when we measure the sizes of things, we don't actually measure the size of things, we measure their angular size. So it's called the angular diameter. And it turns out if you hold your pinky up at arm's length, that's about 1/2 degree. Now you need those special glasses I sent you, but if you put on those special glasses and you hold up your pinky, you'll notice that you can blot out the sun with just your pinky. It's much smaller than you might have thought. Those glasses make it safe to do this, by the way. Don't do it in any other way. So both the moon and the sun are about the same angular diameter, about 1/2 degree. If you hold your fist up, your fist, right? The fifth is about 10 degrees. This is about 15 degrees. And this is about 25 degrees. Okay, you don't need to know all of those. But anyways, analemma is an interesting pattern that we see. If you take a picture of the sun at the same exact time every day for a year, it will make a figure 8 shape in the sky, in the sky. And then the second time, this is actually something important that I want to share with you. In the winter, the sun travels on a lower path, and in the summer, the sun travels on a higher path. So we're going to watch the sun together for a year, and we're going to see an amazing pattern. And I think that you will be really amazed when you understand what this pattern shows us. So let's go ahead and do that. We're going to go ahead and watch the sun for a year. And I will be giving you a group activity where you have to do a little bit more detail. But today, the main thing is I want to talk about the 4 seasonal dates. Okay, so I'm going to go ahead and write those down on my piece of paper. And you need to write them down. These are the 4 seasonal dates that you need to know, right? So the first seasonal date is 3/12/2022. 321, 321, right? Why am I writing it like that? Forget that. Let's put 321. That's what I meant to write. Okay, so the date, 321. And what we're going to be trying to talk about is at noon, right? At noon, the sun's altitude. What is the sun's altitude at noon? And then the last thing I do want to point out to you is how many hours of sunlight do you get? Okay. Oh, I forgot I was going to also, I need to tell you the name, right? What's the name? So we need a name right here. Let's put the name right here. So I'm going to give you a name. I'm going to tell you the date. And there's 4 of these that you have to memorize. We're going to talk about the sun's altitude and the hours of sunlight. So the 4 dates, let's write the 4 dates down. 321, 621, 921, and 1221. Those are the 4 dates, okay? What is the name that we give for 321? This is called the vernal means spring, equinox. 621 in Santa Barbara, it's actually this is Santa Barbara. Let's put that down, Santa Barbara. Now, what's important about Santa Barbara, you may or may not know this already, but I'm going to tell you that this is important, is that we are 34 degrees north latitude. You need to write that down because that's actually an important fact for our observations that we're going to do right here. Okay, so the vernal equinox is 321. What is 621 called? That is called the summer solstice. Okay, 921 is called the autumnal equinox, and 1221 is the winter solstice. Okay, so those are our 4 dates, and what we're going to do is we're going to watch the sun on each of these 4 dates, and we're going to answer the question, what was the sun's altitude at noon, and how many hours was the sun in the sky? Okay, so let's go ahead and switch to our stellarium, and we're going to change the date. Look at how easy this is, 321, here we go. Now, I'm actually going to show you guys another little piece of this. This is kind of important. So I apologize, I'm just adding this in all of a sudden. I want to go ahead and put on this one more line. I'm going to put on the celestial equator. So we have it right here. Let's turn on the celestial equator. I want you to notice something important. Where is the sun on 321? If you notice, it's not exactly perfect. Let me go back to 320. That a little bit better. Actually, 319 this year is even better. I want you to notice that the sun is right on the celestial equator on 319 this year. So the dates that we're memorizing are not perfect. They're just meant to be an easy way to memorize the dates. But it's always close, like within a few days, right? 1 or 2 days usually, okay? And so on this date, we're going to cross the local meridian. It's going to take a few more minutes. And we're looking for an azimuth of 180 degrees. There it is. I've got it right there. Let's go ahead and write down 55 degrees and 27 minutes and 57 seconds. Now, just to be friendly, I'm going to tell you that I'm going to call that 55 degrees and 30 minutes. And 30 minutes, by the way, is exactly half of a degree. So go ahead and let's write down that the sun's altitude was 55.5 degrees. Okay, that's what it was. Now that's interesting. I probably need to show you something else, but anyways, okay, coming back to that later. How many hours of sunlight? So it turns out that this software tells me that, or I can just kind of work it out independently. I think I'm just going to go ahead and do that with you. If I go back to the software, I could just count back how many hours before it gets to the sun, the horizon. Okay, so 1, 2, 3, 4, 5, 6 hours. And if I had moved forward 1, 2, 3, 4, 5, 6 hours. So what you should notice is that it's about 12 hours of sun, 12 hours of sunlight. Actually, it says daytime, 12 hours and 9 minutes. Let's go with 12 hours, okay? So if you would, let's go ahead and write in 12 hours. And think about that for a moment. Why is it called the equinox, right? What does equinox mean? Equinox means literally equal night. So what's equal to night? Day is equal to night. And so you have 12 hours of day and 12 hours of night. Together that makes 24 hours. So day and night are equal on the equinox. Okay, we got the angle 55.5 degrees. Okay, back to our software. Okay, what's the next date? The next date in our sequence is 6/21. Go ahead, 6/21. And you'll notice something. I want to go back to noon again, right? What do you notice? The sun is higher or lower in the sky? And remember, it was on the celestial equator on the equinox, but now it's above the celestial equator. Let's look for the azimuth, 186. So I'm just going to back it up just a few minutes. Oh, there was 180. Okay, about 180. Actually, 179.34 is closer. Okay, so, and I can look right here, the altitude 79 degrees. So you can write that. Actually, before we do that, how many hours of sunshine? So I'm going to go back 1, 2, 3, 4, 5, 6, 7, right? And 1, 2, 3, 4, 5, 6, 7 more, right? So that's a total of about 14 hours of sunshine. Okay, so let's see, what were our two numbers? We got an angle up here of 79 degrees, and we got 14 hours of sunlight, 14 hours. This is why in the summertime we have so much time to do all those fun things, right? Summertime, lots and lots of fun. Okay, so back to our simulation. Go to our next date in line. So that's going to be 9/21. Now, I want to ask you, looking carefully, is this the right date? So let's see, is this better or worse? That looks a little bit better. It's a little bit closer. So about 9/22 this year is actually going to be the equinox, okay? And I need to back up just a few minutes there until I get to 180. There it is, okay? And what's the altitude? 55 degrees and 28 minutes. Again, it's about 55.5 degrees. In other words, the same thing it was before. So on the equinox, where is the sun? It is on the celestial equator. So I don't need to do it again because it's exactly the same as it was before. But if I did, it would be 1, 2, 3, 4, 5, 6 hours this way and 6 hours going forward. Okay, so a total of 12 hours. Go ahead and put that in. So we went back to the equinox and we got the same result, 55.5 degrees, and we got 12 hours. So our last one is the winter solstice. So here we go, our final one, the winter solstice. We are going to move forward to 12/21. 12/21. You'll notice that the sun is a lot lower in the sky. By the way, daylight saving is over. So we're going to go back. It'll be closer to actual noon. And we'll roll forward until we see 180 degrees for the azimuth right there. Good, good, good. And our altitude is 32 degrees, 10 minutes, we'll call it 32 degrees. Now this one is a little bit harder to measure the time for. I actually feel like I should just look. Yeah, I'm just going to look right here. It says 9 hours and 52 minutes. You know what? I'm going to call that 10 hours, but it's actually a little bit less than 9 hours. That's okay. We'll call it 10 hours. Okay. So we had an altitude of only 32 degrees above the horizon and a time of about 10 hours. Okay. So the last part of this is the most exciting part. This is the part that I just think is the coolest thing ever. And by the way, you could do this anywhere on Earth, and the numbers are going to change because they depend on where you are, your latitude. But if you do what I'm about to do, you will always get the same result. Let's take the biggest number and the smallest number and subtract them. So 79 minus 32. Okay, and this is amazing. What's 9 minus 2? 9 minus 2 is 7. 7 minus 3 is 47 degrees. Wow. Wow. It's just amazing. That is amazing. I'm sure all of you know about the 47 degrees. Isn't that amazing? Okay, so I'm just joking because most people at this point are saying, what the heck is going on? Well, this was the biggest angle and this was the smallest angle, but don't forget, we had the equinox in between. So it's really 2 steps, right? A step down to here and then a step down to here. So take this number and divide it in half. What is 47 divided by 2? And the answer is 23.5 degrees. You need to memorize that number because this is in fact the tilt of the Earth axis. Okay, and so that is why it's so amazing. The reason why the sun goes higher and lower in the sky is because of the tilt of the Earth axis. Okay, so this is the angle, right? So here is Earth, and you notice that it's tilted, right? It's not vertical, it's tilted. And that angle of tilt is 23.5 degrees. You need to memorize that. That is something special for Earth, okay? So back to our slideshow. So the sun is higher in the summer and lower in the winter. So there's a couple of things to recognize, right? If the sun is higher, it actually is following a longer path through the sky, which is why it takes longer to go through the sky. But there's something else that's really critical. In the summertime, when the sun is higher, what happens to the intensity of the sunlight? And you probably know this from experience, you're more likely to get burned in the summer than you are in the winter because the sunlight is more intense. So what is summertime? You get longer days because the sun is higher in the sky and takes a longer path with more intense sunlight, more direct sunlight. In the winter time, the days are shorter because the sun takes a shorter path and the sunlight is less intense sunlight, right? That's a reason for, this is the reason for the seasons. Okay, so a couple of things just to note, right? Remember the celestial equator comes out of the east and goes into the west. So where does the sun rise? Well, on March 21st, exactly in the east. On June 21st, it's going to be to the north of east so that it can take the bigger, longer path. When it's September 21st, it's back to rising in the east. And December 21st, it's way to the south of east. Okay, and this is true no matter where you are on Earth, right? No matter where you are, this is what the sun will do. It will rise in these positions. And ancient people must have known this, right? And they marked those. That's why Newgrange is able to see the winter solstice because the sun is just the right angle to enter the corridor of Newgrange. Okay, so here is a picture that you need to recognize. This is the Earth, and by the way, the arrows show you the correct direction, which is also the direction the Earth is rotating, the direction the moon goes around the Earth, the same thing. What an interesting coincidence. But the Earth is going around the sun in this way. This takes 1 year to go fully around, okay? If you notice, the axis of the Earth is always pointed off in this direction towards the star called Polaris, the North Star, okay? But the idea is in the summertime, the northern hemisphere has summer, but the southern hemisphere has winter, the same day of the year. So 621 is right here. This is 621. So 621, the Earth is tilted towards the sun. We have longer days, more direct sunshine. As we continue, the next date that we come to, 621, this would be 921. And now you want to recognize that the tilt of the Earth is not towards the sun or away from the sun. And that's why we don't have longer days or shorter days. We have 12-hour days and 12-hour nights. We continue, and in this picture, this is going to be 1221. In the northern hemisphere, we're tilted away from the sun. The sun is going to be lower in the sky, shorter days, and less intense sunlight. But in the southern hemisphere, if you flip over, they're having their summertime, the opposite seasons. So this one was fall in the northern hemisphere, but it's spring in the southern hemisphere. So let's see, summer in the northern hemisphere is winter in the southern hemisphere. Fall in the northern hemisphere is spring in the southern hemisphere. Winter in the northern hemisphere is summer in the southern hemisphere. Our last one, 321, we're not tilted towards or away. So again, it's an equinox. And this time we have the vernal equinox in the northern hemisphere and the autumnal equinox in the southern hemisphere. This picture will be on your next test. Make sure you recognize it. Okay, so here's the picture again, trying to give you an idea. In the wintertime, the sunlight is more spread out when it hits the ground. It's like a flashlight almost. Imagine a flashlight. It's more spread out, so the intensity is smaller, and then more concentrated, the intensity is larger. Okay, so summertime is summer because you have longer days with more intense sunlight, and winter is winter because you have shorter days with less intense sunlight. Okay, so we have these stars in the sky, and for time, ever since human beings began to look at the stars, they began to find shapes in them, and these shapes are called constellations. So in 1932, the IAU, the International Astronomical Union, defined 88 constellations. There are 88 different constellations in the sky. And these constellations have been used as a calendar for a very long time. This is where astrology got the idea of using the constellations. And now they can just use a calendar instead of the constellations. In fact, that's what they do. These are some famous ones. Sagittarius. This is, by the way, the Milky Way, goes right to the middle of them. There's another part of the Milky Way. This is the center of the Milky Way over here. We'll talk more about that later in the course. When you look away from the center, you're looking at the far side of the Milky Way, away from the center. It's much less dense, much not as bright. Okay, so there are 88 constellations. Can we see all those constellations in Santa Barbara? And the answer is nope, not all of them. There's some that we cannot see. So I will show you that in just a moment. Okay, so now there are constellations that are near the pole that never rise or set. Those are called circumpolar constellations. Now, this is an interesting idea. The sun is going to follow a path through the sky that we call the ecliptic. You should write that down. That's a good definition to know right now. There's another definition of ecliptic, but this one is the one that we want to use today. And the sun will go through different constellations during the year. And traditionally, there were 12, but if you look today, there are actually 13 zodiac constellations. I'll mention that to you in just a minute. But anyways, these are the constellations the sun goes through. And the way it works is as the Earth goes around the sun, right, when we look at the sun, we see it in different constellations, right? As the Earth moves, the sun will appear to move. Now, everybody knows how many degrees there are in a full circle. How many degrees? And the answer, of course, is 360. And how long does it take the Earth to go once around the sun? And you might also know 365 days. Now, did you ever think that those two numbers are pretty close? Isn't that kind of interesting? You don't need to know, but it's kind of a cool fact that the Babylonian calendar counted 360 days. And you're like, well, that's pretty good. Babylonians were pretty close. They were only 5 days off. But you know what? They knew exactly how long a year was. Their calendar only counted 360 days. At the end of every year would be 5 days of celebration where they didn't count them. It wasn't part of their calendar, but they loved the 360 so much that they made it that. And they're the reason why we have 360 degrees in a full circle. But it is not a coincidence that there's 360. It has to do with the length of a year. Okay. So one of the quick little things we could say is when we talk about the Earth going around the sun, you could ask how many degrees does the Earth go around the sun every day? And because 360 is pretty close to 365, you could say the Earth goes about 1 degree in its orbit around the sun, in its revolution around the sun. When we look at the sun appears to move along this red line called the ecliptic about 1 degree per day, right? So every day it's moving just one little step, and it takes a full year to come back to where it started. Okay, so I'm going to show you these zodiac constellations right now. Oops, let's go ahead and show you with Stellarium. And so let's go back to our current date, just so you can kind of see a full cycle. Okay, so today is the 5/21. Perfect. Okay, and I'm going to show you the celestial equator. I can turn off the meridian. I don't need the meridian, but I do want to show you the ecliptic. Okay, so remember the ecliptic is the path that the sun follows. I'm going to turn off the ground and the atmosphere. And then the fun part, let's go ahead and fun part, let's turn on the constellations. So if you just slide down here, here is the lines for the constellations. and here are the names, and here's the artwork. And so as you look around the celestial sphere, you can see there are 88 different constellations, right? So many different constellations to look at, 88 of them in all. Okay. Wow, I'm getting confused. Okay, and I don't know where's the sun? Where is the sun? Oh, there it is. Okay. Okay, so here's our sun. And so what we want to do is we want to watch the sun. So we're going to focus on the sun, and you press space bar when you click on something, and that will center it and make it follow it. And what we're going to do is I'm going to watch the sun move through constellations. So right now, actually, I'll do one more thing. You go over here to viewing options. You can go to the star lore and show boundaries, and I'll change the color to something a little brighter. And so we can see the boundaries of the constellation. So right now the sun is in the constellation of Taurus, the bull, okay? I'm gonna go ahead and move forward, and I'm gonna hold this down, and you can see that the sun is moving little by little through the constellations along this path that we call the ecliptic. Now this path is actually not the same as the celestial equator, right? In fact, you can see that this path is above the equator right now. We call it a positive declination. Let me say one more time, I'll center the sun and moving forward, right? So 621 is as far away as it gets from the celestial equator. And then it's going to start to move closer to the celestial equator. So every day it moves a little bit along its path, every single day. And so actually in astrology, the day you were born, the sun is in a constellation. That's called your sun sign. That's your sign, right? That's supposed to be where the sun is located. So as you go along here, you'll see there's Leo, there was Cancer, Leo. The next one up comes Virgo, and then we're still in Virgo, okay. Next comes Libra. Okay, now, here's where the new constellation comes in. So if you are born between November 29th and about December 17th, then there's a little gap in the traditional constellations. So the constellations the sun is going through are called the zodiac constellation. But in between Scorpius and Sagittarius, there is a gap now, right? And that's because of the 1932 definition of the boundaries. And in Japan, they actually do this. This is the legitimate astrology in Japan. They have a 13th zodiac sign. It's known as Ophiuchus, okay? And that is the serpent bearer, right? So there's a serpent holding guy, Ophiuchus. I happen to be born in this period. So anybody in this boat with me, we're in the 13th zodiac sign, okay? So as you follow this through a full cycle, the sun will pass through all of these 12 constellations, now 13. And when it comes back after a year, it will go back to the same position it was the year before. Then you know a year has passed. So ancient people knew that a year had passed because they came back to the same position. The sun came back to the same position in the sky. But here we are, we're back in Taurus, the bull, 5/21/2021. It's back to the same position. Okay, a year has passed. Now, we mentioned that there are some constellations that are going to be visible all night long. These are called circumpolar constellations. Let me turn the ground on. And oops, let me turn the ground. Oh, there's the ground. There's ground somewhere. I don't see ground. Oh, there it is. There's the ground. Okay, let's look to the north. And I want to show you as I zoom out, right? If I go ahead and start playing this, you can see that some constellations are going to be visible all the time, right? Those are the circumpolar constellations. So in Santa Barbara, there's a few constellations, just a handful. This one's really cool, Camel Leopardus. Everybody know the camel leopard with the big long neck? That was the old name for a giraffe, camel leopard. But we have a handful of constellations that are circumpolar. But you know that if you go to different places on Earth, you can see something very different. So if I pause this and go back to today's date, just to show you today's date right now, if I go to another location on Earth, and I'm going to go to a very specific place, I'm going to go to 90 degrees. I'm going to go to 90 degrees. Okay. Anybody know what that would be? 90 degrees north latitude. Where am I? And you would say, I am where? I am at the North Pole. So right above my head, I'm going to find the star called Polaris, right above my head. Okay. So right above my head is the star Polaris at the North Pole. And this is going to be kind of a funny thing, right? So how many constellations can be seen all night long? Well, so let's go ahead and close this up and start the clock. And the answer is, well, all the constellations can be seen, right? They're going to be just circling around Polaris. So about how many? And the answer is about 44. About 44 of the constellations can be seen. So the number of circumpolar constellations will change depending on where you are on Earth. Now, it's kind of a cool thing also to notice, something weird. If you're at the North Pole right now today, is the sun up? And the answer is absolutely. And something really weird, look what the sun is doing. It's just circling around the sky. Now, the program really does something funny, and I actually think it's so cute that it does this. But if you are standing on the North Pole and you take one step, which way are you going? And the answer is you can't go north of the North Pole, right? So every direction that you look is actually south of you. That's cute. The program is showing you that, right? Every direction is south. So the sun just circles around. In fact, it doesn't set. So what's really important for you, you should know this, by the way, is that the sun came up, and what's happening is the celestial equator is actually the same as the horizon line. And so if you remember, on what date does the sun cross the celestial equator? And the answer is on 3/21. And so if I went back to about 3/21, you'd see the sun is just poking up above the horizon. And so it's going to be up for the next 6 months until finally 9/21, it's going to be setting again. So if you're at the North Pole, daytime starts on March 21st and lasts until 9/21. And for 3 weeks, maybe even a month, if I turn on the atmosphere, you can actually see that even, well, maybe not, actually it's pretty much, maybe a few weeks. How about that? For a few weeks, you're still going to see the light of the sun. It'll be twilight, right? So, but basically they have a 6-month day followed by a 6-month night. Now, it's the opposite for the Southern Hemisphere, right? In the Southern Hemisphere, the sun will go away and it'll become nighttime on 3/21, and it will last until 9/21, and then the sun will be rising in from the southern pole, South Pole, okay? All righty, so those are some cool things you can see. Let's go back to our PowerPoint. What did I do? I lost my power, lost it. No, let's try to get it back again. I lost my PowerPoint somehow. I don't know what I did. Here we go. Go back to our PowerPoint. All right, so we mentioned the ecliptic, the path the sun follows. The zodiac are the constellations that the sun goes through during the year, and there's actually 13. Make sure you know that. That could be a good question for the quiz and the test. All right, let's keep moving. So now, next up, we want to talk about the moon. And in fact, the moon has been important as well for telling time. In fact, some cultures use a lunar calendar. A lunar calendar uses the moon cycle to keep track of time. And the word month actually comes from one lunar cycle. So you need to know something. The moon is going around the Earth. It revolves around the Earth. And it also, as it does, it gets in between us and the sun, and we have phases of the moon based on the location of the Earth, moon, and sun, right? So sun, Earth, moon angle is basically how it works. So when the moon is lined up with the sun, we have a new moon. As it slides, it goes around in this direction. As it goes around between this angle and this angle, you'll see just a part of the moon lit up. It's called a waxing crescent. And here we have our first quarter moon, okay? And there's a 90-degree angle between the sun and the moon here. with the Earth at the vertex. When you go and keep going, you start to get more than halfway lit up. It's called a waxing gibbous. And finally get to full moon. The full moon is across from the sun, right? Across from the sun. And then if you keep going, now it's going to be less than fully lit up. It's called a waning gibbous. The left-hand side is lit up this time, and the right has the darkness. It was the opposite for waxing, right? Keep going, and it's a 90-degree angle. It's actually called 270 degrees, but anyways, this is called the third quarter moon. And then keep going, we got a waning crescent and back to new moon. So there's two words here you want to write down. One is called a sidereal month, and the sidereal month means relative to the stars. And then there is synodic month, relative to the sun. Okay, you need to know both of those words. So you want to write that down. So it's about 20, actually it says synodic month is 30 days. It's actually 29.5 days. I'm just gonna stop. Let me write this down. So you need to know the numbers a little bit better than that. So, okay, so one is called sidereal month. It's actually 27.3 days. Okay, what is that? The time it takes, time for the moon to orbit once around Earth. Okay, so that's one orbit around the Earth. Okay, so why isn't that the same as a synodic month? And the answer is because a synodic month is based on the sun, right? It's 29.5 days, which is very close to 30 days, about 30 days. And it is the time for one complete lunar cycle. So what does that mean? From full moon, for example, to full moon, or from new moon to new moon, right? So it doesn't matter where you start. It's from full moon to full moon or new moon to new moon. So that time is what we call a lunar cycle, synodic month, okay? So why aren't they the same thing? Well, because the Earth doesn't stand still. So actually just to look at the picture, back to the slide set again. In one cycle, one lunar cycle, let's say we have a new moon, right? The moon goes around the Earth goes towards, in this direction around the sun. In 1 month, right, the moon comes back to where it started. But when it comes back to where it started here, it's actually not lined up with the sun yet, okay? And so this is what we call one sidereal month, when it comes back after doing a 360 degrees. Remember, this took 27 days, right? So it turns out that actually the moon has to move a little bit further to line up with the sun again. And so how far did the Earth go in about 27.3 days? And the answer is about 27 degrees. And so the moon has to travel an extra 27 degrees to get lined up with the sun, actually even a little bit more, because it's going to take a couple more days to do that. So it's going to end up almost 30 degrees more. So that's about 1/12 of a full circle. And so that's going to take another 2.5 days, right? Almost 2.5 days, 2.2 days. Okay, so the idea is the moon goes around in 27 days, but it doesn't get back to a new moon until 29.5 days. All right, so you've heard about this thing called an eclipse. What's an eclipse? There's two kinds of eclipses. One is called a lunar eclipse. That means that the moon goes into the shadow of the Earth. And the other is called a solar eclipse, where somebody is in the shadow of the moon. You're on the Earth, and basically the sun is being blocked by the moon, okay? So actually, before we get into that completely, let's talk about shadows, because you need to know that. This is an important concept, shadows, right? So the sun is pretty big, right? The sun is pretty big. And whatever it is, either the Earth or the moon is going to be smaller. And so if I were asking myself, what does a shadow look like? And I just took this one spot on the sun, I could draw a little picture, and I'm going to just draw it freehand, so it's not going to look that pretty. But the idea is that the sunlight will hit that object, and there will be a shadow behind, right? There's a shadow here. But really, sunlight comes from every place on the sun. Now, we don't actually need to go to every place. It turns out we just need to go along a vertical line. And we don't actually even need to take it from every point. We're just going to use the extreme points. I'm going to try to make a shadow from the top and from the bottom. Okay, these are the extreme places that are going to make the shadow on the Earth. I'm going to do it again. And the picture that I get is going to be really helpful for me to understand how shadows work. So you'll see that the shadow that is made by one part of the sun is not the same as the shadow made by another part of the sun. But part of the shadow is always shadow, right? So you'll notice that this part right here is always shadow, no matter which part of the sun you're talking about. So this is the best shadow, right? This is called the umbra. The dark part of the shadow is called the umbra. Now, these other regions nearby are partial shadow, right? So their shadow, the shadow here from this part is actually going to get sunlight from this part. So these are not very dark. These regions right here are not very dark. They're called the penumbra. So when I ask you the question, which part is the darkest part of the shadow? The answer is the umbra. And the penumbra is not really, it's a partial, let's put partial shadow. So it's not as bright as full sunlight, but it's definitely not as dark as the umbra, not even close, okay? All right, so that is needed for talking about eclipses. When we talk about eclipses, right, the umbra is the darkest part of the shadow. The penumbra is not really noticeable. If the moon is entering the penumbra, you actually can't tell. It'll dim just slightly, but your eye will open a little bit more to see the light, and you will not be able to see it. So if you hear somebody say, oh, there's a penumbral lunar eclipse, I mean, if you want to go look at the full moon, that's great. But otherwise, waste of time, total waste of time. You're not going to see anything happen. You really want to see an umbral lunar eclipse, and those are going to be really cool. You'll see a big chunk taken out of the moon. It's really wonderful. Okay, so let's take a look at the phase of the moon, right? So remember how it worked? If the moon was between the Earth and the sun, that was a new moon. But if the moon is on the far side of the Earth, which is what it has to be when it enters the shadow of the Earth, it is a full moon. So you can only get a lunar eclipse with a full moon, okay? A solar eclipse can only happen with a new moon. Okay, so we know that the phase has to match to get it. So do we have eclipses every month? And I know you probably know the answer is no, we do not. Why don't we? Why don't we have eclipses every month? And the answer is because the objects, the sun, the moon, and the earth do not line up perfectly. Speaking of that, there's actually a really cool word, and you don't need to know this at all. I just think it's the coolest word. Can I just write it down for you? What do you call the alignment of planets? Like three for one, right? What do you call it when the earth, the sun, the moon, and the sun are aligned, right? What do we call that? The alignment of two or more objects. Ready? It's called a syzygy. Syzygy, right? So the alignment of two or more, it's actually the alignment, conjunction of two or more bodies. Two or more bodies. It's just a cool word. So if you know that word, if you've seen that word before, then you know what it means. But you only get an eclipse when there's a syzygy, right? You only get it with a syzygy. So does it happen all the time? The answer is nope, it does not. And here's why. Actually, sorry, next slide. You're going to get that in a second. Okay, so tiny little details, just a little bit of detail. The moon is going around the Earth. And so if you take a look right here, there's two words. The path that the moon follows is an elliptical path. And there are two words here. One is called perigee and one is called apogee. What do you notice about the size of the moon here? And you might notice that the moon is a little bit bigger at perigee and a little bit smaller at apogee. And it turns out the Earth is going around the sun. So hold on, I gotta show you some pictures here. Okay, so let's put the Earth in the middle, And then I'm going to show you, I'm going to exaggerate it, but exaggerate the moon going around the Earth. This is an elliptical path, elliptical orbit. Real orbits are elliptical. I've exaggerated. This is not really the case. It's really much closer together, but I just want to give you that idea. So this is the symbol. A cross is the symbol for the Earth. And then a little crescent like this is the symbol for the moon, okay? And when you're closest to the Earth, this is called perigee. Now, G is short for geo, which means Earth. Perigee is closest to the Earth, right? This is perigee. And when you're furthest from the Earth, right, the moon is furthest from the Earth, this is called apogee. Apogee, again, G means Earth, right? So what happens to the size of the moon? When it's at perigee, it's a little bit bigger. When it's at apogee, it's a little bit smaller. Now, it turns out that the Earth is also moving around the sun. There's a symbol for the sun on an elliptical orbit. We're going to exaggerate, right? It's really not at all like this. It's almost a perfect circle, but just want to exaggerate. And so now I'm going to show you the Earth closest to the sun. What is the word for that? Well, that word is called perihelion. I'm going to write that down. That means closest to helios, which is the Greek word for the sun. Perihelion is when you're closest to the sun. And the word for when you're furthest from the sun is called aphelion. You need to know those words. Okay, so perihelion, aphelion, closest to the sun, furthest from the sun. So when the Earth is closest to the sun, what happens to the size of the sun? And the answer is the sun gets a little bit bigger. Okay, at aphelion, what happens? The sun gets a little bit smaller. Okay, so back to our cool picture here. This is a very cool picture. This is called an annular. You can write that down. An annulus means a ring. An annular solar eclipse. It's not an annual. It's not the word annual. It's annular, means a ring. So can you tell me why it's a ring, right? The moon is in front of the sun, but it's not the right size, right? Is it a little big or a little bit small? So there's actually two possibilities, or maybe both, right? Maybe the sun is a little big, or maybe this moon is a little small. So just keep it in mind. How do you make a small moon? And the answer is the moon is at apogee. And how do you make a big sun? The Earth is at perihelion, right? See how I had to talk about the Earth because the sun actually doesn't move. Okay, so it turns out that to get a total eclipse, all of the light of the sun must be blocked. So now actually keep in mind, this may be a question on your test. How do you get a long solar eclipse? Well, the answer is when the moon is really good at blocking the sun. So in that case, you want a big moon and a small sun. Well, how do you get a big moon? Where would the moon be? The moon will be at perigee. How do you get a small sun? And the answer is the Earth will be at aphelion, and then you can get a longer lunar eclipse. Okay, so why do we have eclipses every month? And here is the reason why. The moon's orbit around the Earth is not exactly in the same plane. It's tilted by about 5 degrees, okay? And I would like you to write that down, 5 degrees. But anyways, the moon basically is going to ride above and below the plane that the Earth and the moon are in. This is a mathematical plane, okay? So it turns out in order to have this perfect alignment, syzygy, you have to not only have the right phase of the moon, but it has to be at the right height, right? It has to be at the level of the moon and the sun, the Earth and the sun, in the plane of the eclipse. So what we call the moon, when it goes through this orbit, the points where it crosses the plane, which is also known as the ecliptic plane, are called nodes, right? And so these nodes are there, right? There's 2 nodes per month, right? The moon goes down through a node as it crosses below the ecliptic plane, and then back up through the node right here as it goes up above the ecliptic plane. But you have to have a node and you have to have the right phase of the moon. And so it has to be just perfect. And this only happens in what are called eclipse seasons, about every 6 months. Okay, here is eclipses coming up for the next few years, for the next 10 years. And the shadow that we see these are solar eclipses, of course. And you can see that you don't always get the right eclipse. So June 21st, hey, it's going to be an annular solar eclipse, but it's only going to be visible in a certain part of the world, right? So in the Middle East, in Africa, the Middle East, in Himalayas, and into Asia here, right? But if you're on this path, then the moon's shadow will touch the Earth, and you'll be able to see an annular solar eclipse, which means it's not going to be completely covered. December 14th of this year, number 2, there's going to be a total solar eclipse, right? So if you're on this path, so not going to be visible to us. Now this one right here is 2024. Okay, so this is the one, April 8th, 2024 is right here. This number, it should say 7, I don't see 7, but you can click on this link, it'll take you to a NASA site. All right, so there is one final idea we're going to talk about in this, actually a couple of ideas, but this is a pretty big one. When ancient people looked at the sky, they noticed that there were some stars that appeared to move or wander from one constellation to another. And these wandering stars were called planets, right? Planet or planet. So a planet looks like a star, but it changes constellations. And it's not a coincidence. There were 5 of them, right? And so I would like you to know something pretty cool. If you take the 5 planets plus the 1 sun plus the 1 moon, what do you get? 5 plus 1 plus 1. You get 7. Now, does 7, what do you think about with 7? And if you said 7 is a lucky number, you are correct, but why? And the answer is there are 7 days of the week. Each day of the week is named for either the sun, the moon, or one of the 5 visible planets, right? So I would like you to know, let's start off with the Sunday, which is kind of obvious, right? The day of the sun. Sunday, what's the next day? Monday or Moon Day. Actually, I want you to start calling it Moon Day, right? The day of the moon. Now, if you know Spanish or Italian or some Latin language, French, right? The next one is actually, even this one would have been easy. Lunes in Spanish, the day of the moon. What about Tuesday, right? How do you say Tuesday in Spanish? And I have to write. Okay, so in Spanish, it is martes. Martes, what day is that? This is the day of Mars, right? Of Mars. Mars is one of the 5 visible planets. How about Wednesday? Wednesday, miércoles. I might be spelling that wrong, sorry about that. But it is the day of Mercury. Okay, Thursday, actually called Thursday, right? Thursday. So actually you need to know jueves. Am I spelling it? Jueves, there we go. Jueves, okay. And you would need to know Jove, which is another name for Jupiter. It's the day of Jupiter. Okay, Friday. What's Friday? Viernes. Viernes, right? Am I spelling that right? Viernes is the day of Venus. And Saturday, well, you can almost hear that one. And actually in English, it's probably easier. Sábado, I don't know how that works, but anyways, it's the day of Saturn. So Saturn day. So these are the 5 planets that could be seen. So if you didn't know it already, you probably should, right? If I take the sun right here, which planet is closest to the sun? Mercury. What's the next planet? Venus. The third planet, Earth. The fourth planet, Mars. The fifth planet, Jupiter. And the sixth planet, Saturn. And so these were the planets that the ancient people could see, right? The planets that were closer to the sun than we were, Mercury and Venus, and then Mars, Jupiter, Saturn. So that's 5 altogether. So 7 days of the week come from the 7 wandering planets. Now, I actually think I should just show you something cool here. So let's go ahead and let's take a look. Let's go ahead and let's turn off these lines of constellations. I don't think we need all that. Turn those off. And actually, I'm going to turn off the words and the art, but leave the lines on. It's kind of cool. I'm going to go to the current date because actually it's kind of a neat thing to see. I'm just going to make it go a little bit later at nighttime. Where am I? Oh, I'm in the wrong place. Sorry about that. Let me go back home. Got to go back to home. Santa Barbara, Santa Barbara, United States. Okay, that's it. Now it's nighttime. Okay, let's go look up. So you can slide over here. There's a search window. Put in Mars, and there's Mars. Okay, now I can't quite see it. Let's go a little bit later. There we go. There's Mars. Okay, actually, let me go ahead and turn off the atmosphere. Okay, so there's Mars, and I want you to see. Actually, I guess we can turn on the names. Let's turn on the name. It's in Aquarius right now. Okay. What I want you to notice is that as days go by, Mars is going to move, right? Mars is going to move. By the way, if you get up in the morning, Mars, Saturn, and Jupiter are almost in a perfect line along the ecliptic, right? Not perfect, but almost. Okay, so as days go by, watch what happens to the planet Mars, right? It took a little tiny step, little tiny step, little tiny step, little tiny step. Which way is it moving? And the answer is it's moving towards the east. That's the normal direction that Mars appears to move. And that's called prograde motion, prograde motion. So if I just hold this down, you can see little by little, look at it, Mars, look at it go, look at it go, look at it go. Well, wait, something's happening. Mars is going higher in the sky, but that's okay. But I do want you to notice something, right? Is it slowing down? Maybe it's slowing down. I don't know. Is it still going to the east? Kind of hard to tell. Seems like it's still going to the east. Still going to the east. Yeah, still going to the east. But at some point, something interesting is going to start to happen. It's not going to go to the east anymore. And I realized what I could have done. I could have done this thing, okay? So what's going to happen is it's actually going to begin, I think you can start to see it. It's going backwards. So what do you call it? Turn off the ground. What do you call it when Mars goes backwards? That is called retrograde motion. So Mars is going retrograde, and now here it is a little bit later, goes back to being prograde. And so we see this with all the planets, right? That most of the time they go in one direction, prograde motion, but then occasionally, depending on the planet, they will go backwards. And it's usually about once a year, but again, it does depend on the planet, okay? So the retrograde motion is an interesting fact that people noticed, right? They noticed that it seemed to go backwards sometimes. Okay, so back to our slideshow, or back to our PowerPoint. Okay, this is what I was kind of telling you. The normal motion of Mars is towards the east, and the retrograde motion is backwards. It does take a long time to watch this. This is one version. This is from a few years ago. And anyways, it's going forward to the east and then backwards, retrograde motion, then back to the prograde motion again, okay? So this is something that people noticed a long time ago. This is actually ancient information I'm telling you about. So we're going to go ahead and not talk about Stonehenge and things like that. That probably would have been, they probably are astronomical. They were definitely astronomical observatories for recording the positions of the planets and the stars. But we're going to jump forward to the Greeks. Here's Babylonians, right? We're going to jump forward to the Greeks. And I'll tell you about Pythagoras and Plato and Aristotle. And we want to understand something important in this picture that we have right here. Here's Aristotle. We're actually going to skip past these guys. These were all important people, but we're going to go ahead and skip forward to Aristotle. And there are two things that I want you to understand. Number one, that Aristotle believed that the earth was at the center of the universe and it was not moving. And the reason he gave, which is really very, very interesting, the reason he gave, he says, if the earth was moving, then we would see the stars moving as a result of our motion. And that's called parallax. And because he couldn't see that, he said, we are not moving. Well, he was wrong. The earth is moving. But the reason he was wrong is he didn't have a precise enough instrument to measure the stellar parallax. So it's the movements of the stars are very, very subtle. And it took a couple thousand years before we developed the technology to be able to see the stars moving. But we now can see the stars changing position ever so slightly. Not all the stars either, just the closest ones. But the other thing is, so the earth is at the center. The other thing is that the heavens are beautiful and perfect, right? The perfection of the heavens. He imagined crystal spheres, 55 apparently, crystal spheres to explain the motions of the heavens, okay? And so the heavens are perfect and they're perfect spheres and the earth is at the center. What do you call this theory where the earth is at the center? This is called a geocentric theory, okay? So geocentric theory was the standard model for quite a long time. And so geocentric means earth-centered. That was begun with Aristotle and the thinkers like Aristotle, and then perfected by a man by the name of Ptolemy. Okay, you don't pronounce the P, but please write down Ptolemy. And Ptolemy developed a very advanced model, a geocentric model, which just was able to predict when planets would go retrograde, right? It was pretty cool. How did he do that? Well, he made the Earth in the middle, of course, with the moon going directly around the Earth. But then when you start looking at the planets Mercury, Venus, Mars, etc., you'll notice that there's a blue circle and a gray circle. The blue circle is called the deferent, and the gray circle is called the epicycle. And the planets are going to move on these epicycles. So if you just look at that, just kind of don't worry about the fact this gray circle is going to ride around on the blue circle. If you notice that sometimes on the gray circle, you're going to appear to go backwards, right? And when you're going this way on the gray circle, you are in retrograde motion. And then you go back to normal prograde motion. So what was really successful with this model is it predicted, it was a model that predicted retrograde motion, okay? And it's kind of a complicated model, and it was never really perfect, but it was very good. And, you know, anyways, it was a very good model. So priests could kind of predict when the epicycle period, or the retrograde motion would occur and tell their followers, and then, you know, people were excited and happy. All right, so in the next chapter, we will advance this history from a geocentric model to eventually getting to the sun in the center, which is called the heliocentric model. But that is it for chapter 2. Thank you for listening with me. And I am now going to finish the live stream. Thank you so much.